Hello learners, welcome back to Rush Learning Hub. I hope you have successfully completed Lecture 1, Fundamentals of Environmental Chemistry, where we discussed classification of elements, stoichiometry, Gibbs free energy, chemical potential, chemical kinetics, chemical equilibrium, Henry's law, carbonate system, hydrocarbons and radioisotopes. Today, we begin Lecture 2, Atmospheric Chemistry, one of the most important and high-scoring topics in the UGC NET Environmental Science syllabus. The atmosphere is much more than just the air surrounding our planet. It is a dynamic chemical reactor where thousands of physical and chemical processes occur every second. These processes influence climate, air quality, ecosystems, weather patterns, and even human health. To understand environmental pollution and global environmental challenges, it is essential to understand atmospheric chemistry. In this lecture, we will explore the chemical composition of the atmosphere and examine how different gases interact with one another. We will study atmospheric particles, ions, and free radicals, which play a crucial role in air pollution and atmospheric transformations. We will learn about chemical speciation, a concept that helps us understand the different forms in which chemical substances exist in the environment. We will also discuss the formation of inorganic and organic particulate matter, which are major contributors to air pollution and respiratory diseases. Further, we will examine thermochemical and photochemical reactions occurring in the atmosphere. Photochemical reactions are especially important because sunlight drives many atmospheric processes, including ozone formation and smog development. Another major focus of this lecture will be oxygen chemistry and ozone chemistry. We will understand how ozone is formed naturally in the stratosphere and why it is essential for protecting life on Earth from harmful ultraviolet radiation. We will also study ozone depletion, one of the most significant environmental issues of the modern era. Finally, we will discuss photochemical smog, a common urban air pollution problem that affects millions of people worldwide. By the end of this lecture, you will have a strong understanding of atmospheric chemical processes and their environmental significance. Composition of air, which forms the foundation of atmospheric chemistry. Before understanding atmospheric reactions, air pollution, ozone chemistry, or climate change, it is essential to know what Earth's atmosphere is made of. The atmosphere is a mixture of gases, water vapor, aerosols, and suspended particles surrounding our planet. It is held around Earth by gravitational force and serves as a protective shield that supports life. The atmosphere regulates climate, provides oxygen for respiration, supplies carbon dioxide for photosynthesis, protects us from harmful solar radiation, and maintains suitable environmental conditions for life. Let's first examine the composition of dry air. Dry air refers to atmospheric air after removing water vapor. The major constituent of dry air is nitrogen, represented by N. Nitrogen constitutes approximately 78.08% of the atmosphere. Although nitrogen is the most abundant gas, it is relatively inert under normal conditions and does not directly participate in most biological processes. However, through nitrogen fixation and atmospheric reactions, it becomes available for living organisms. Composition of air, which forms the foundation of atmospheric chemistry. Before understanding atmospheric reactions, air pollution, ozone chemistry, or climate change, it is essential to know what Earth's atmosphere is made of. The atmosphere is a mixture of gases, water vapor, aerosols, and suspended particles surrounding our planet. It is held around Earth by gravitational force and serves as a protective shield that supports life. The atmosphere regulates climate, provides oxygen for respiration, supplies carbon dioxide for photosynthesis, protects us from harmful solar radiation, and maintains suitable environmental conditions for life. Let's first examine the composition of dry air. Dry air refers to atmospheric air after removing water vapor. The major constituent of dry air is nitrogen, represented by N. Nitrogen constitutes approximately 78.08% of the atmosphere. Although nitrogen is the most abundant gas, it is relatively inert under normal conditions and does not directly participate in most biological processes. However, through nitrogen fixation and atmospheric reactions, it becomes available. The second most abundant gas is oxygen, represented by O. Oxygen constitutes approximately 20.95% of the atmosphere. It is essential for respiration, combustion, and numerous biochemical processes. Without oxygen, complex life forms could not survive. The third major component is argon, represented by Ar. Argon contributes approximately 0.93% of atmospheric air. It is an inert noble gas and does not participate significantly in atmospheric reactions. Next comes carbon dioxide, represented by Co. Although carbon dioxide accounts for only about 0.04% of the atmosphere, it plays an extremely important environmental role. Carbon dioxide is a greenhouse gas that regulates Earth's temperature and participates in photosynthesis and the global carbon cycle. For UGC NET examinations, remember this important fact. Even though carbon dioxide exists in very small quantities, it has a disproportionately large influence on climate and environmental processes. In addition to these major gases, the atmosphere contains several trace gases. These include methane, nitrous oxide, ozone, hydrogen, neon, helium, krypton, and xenon. Although present in very low concentrations, trace gases are chemically significant because they influence atmospheric reactions, climate regulation, and air quality. Now let's discuss variable atmospheric constituents. Unlike nitrogen and oxygen, certain atmospheric components vary significantly with time and location. The most important variable constituent is water vapor. Water vapor concentration may range from nearly 0% in cold polar regions to approximately 4% in humid tropical regions. Water vapor is responsible for cloud formation, precipitation, humidity, and weather processes. It is also one of the most important natural greenhouse gases. Another variable constituent is aerosols and atmospheric particles. These include dust, smoke, pollen, sea salt, sulfate particles, soot, and industrial emissions. Aerosols influence climate, cloud formation, visibility, and human health. Pollutant gases such as sulfur dioxide, nitrogen oxides, ammonia, and volatile organic compounds are also variable atmospheric constituents. Their concentrations depend on natural processes and human activities. Now let's discuss some environmentally important trace gases. The first is methane, represented by CH. Methane is a powerful greenhouse gas and contributes significantly to global warming. Major sources include wetlands, rice fields, livestock farming, landfills, and fossil fuel extraction. The second is nitrous oxide, represented by NO. Nitrous oxide is another greenhouse gas and also contributes to stratospheric ozone depletion. The third is ozone, represented by O. Ozone plays two contrasting roles in the atmosphere. Stratospheric ozone protects life by absorbing harmful ultraviolet radiation. However, tropospheric ozone acts as an air pollutant and contributes to photochemical smog. The fourth is sulfur dioxide, represented by SO. Sulfur dioxide contributes to acid rain formation and atmospheric particulate matter. The fifth is nitrogen dioxide, represented by NO. Nitrogen dioxide participates in photochemical smog formation and atmospheric oxidation reactions. The sixth is carbon monoxide, represented by CO. Carbon monoxide is a toxic gas produced by incomplete combustion of fuels. It affects air quality and human health. Now let's understand why atmospheric composition is important in environmental science. The relative abundance of gases determines climate regulation, atmospheric chemistry, ecosystem functioning, and air quality. Small changes in trace gas concentrations can significantly alter environmental conditions. For example, increased carbon dioxide and methane concentrations contribute to global warming. Similarly, elevated sulfur dioxide and nitrogen oxide concentrations contribute to acid rain and smog formation. This is why environmental scientists continuously monitor atmospheric composition. For UGC NET examinations, remember these key facts. Nitrogen is the most abundant atmospheric gas at approximately 78%. Oxygen is the second most abundant gas at approximately 21%. Argon constitutes approximately 0.93%. Carbon dioxide contributes approximately 0.04%. Water vapor is highly variable and can range from 0 to 4%. Trace gases, despite their low concentrations, play major roles in climate regulation and atmospheric chemistry. Let's summarize. Earth's atmosphere is composed mainly of nitrogen and oxygen, along with argon, carbon dioxide, trace gases, water vapor, and aerosols. Nitrogen and oxygen are relatively constant constituents, while water vapor and aerosols vary with environmental conditions. Trace gases such as methane, ozone, nitrous oxide, sulfur dioxide, and nitrogen dioxide are present in small amounts but have enormous environmental significance. Understanding atmospheric composition provides the foundation for studying atmospheric particles, ions, radicals, ozone chemistry, and air pollution processes. Chemical speciation. Chemical speciation is a frequently asked topic in UGC NET Environmental Science because it helps us understand how pollutants behave in the environment. Simply measuring the total concentration of a chemical element is often not enough. Environmental scientists must also know the specific chemical form in which that element exists. This concept is called chemical speciation. Chemical speciation refers to the distribution of an element among different chemical forms or species present in the environment. These species may differ in their physical properties, chemical reactivity, mobility, bioavailability, and toxicity. In simple terms, the same element can exist in multiple chemical forms, and each form behaves differently in the environment. Therefore, environmental impact depends not only on the amount of an element present but also on its chemical species. Let's understand this with an example. Consider sulfur. Sulfur may exist as sulfur dioxide, sulfur trioxide, sulfuric acid, sulfate ions, or sulfate aerosols. Although all contain sulfur, each species has different environmental behavior and impacts. Sulfur dioxide contributes to air pollution. Sulfuric acid causes acid rain. Sulfate aerosols influence climate and visibility. This clearly demonstrates the importance of chemical speciation. Now let's look at some atmospheric examples. Nitrogen can exist as nitric oxide, nitrogen dioxide, nitric acid, ammonia, nitrate ions, and ammonium aerosols. Each species participates in different atmospheric reactions. Nitrogen dioxide contributes to photochemical smog. Nitric acid contributes to acid deposition. Ammonium compounds are important components of atmospheric particulate matter. Similarly, carbon can exist as carbon monoxide, carbon dioxide, methane, and volatile organic compounds. Each form has distinct environmental significance. Carbon monoxide is toxic to humans. Carbon dioxide is a greenhouse gas. Methane is a powerful greenhouse gas with high global warming potential. Volatile organic compounds participate in photochemical smog formation. Let's now discuss the factors that influence chemical speciation. The first factor is pH. The acidity or alkalinity of the environment strongly affects the chemical form of many elements. Changes in pH can alter solubility, mobility, and toxicity. The second factor is redox potential, also known as oxidation reduction potential. Redox conditions determine whether elements exist in oxidized or reduced forms. For example, iron may exist as ferrous iron or ferric iron depending on redox conditions. The third factor is temperature. Temperature affects reaction rates and equilibrium conditions, influencing species distribution. The fourth factor is sunlight and ultraviolet radiation. Photochemical reactions can transform one species into another. For example, nitrogen dioxide undergoes photolysis under sunlight, producing reactive oxygen species. The fifth factor is the presence of oxidants and ligands. Substances such as hydroxyl radicals, ozone, nitrate radicals, chloride ions, and organic ligands influence chemical transformations. Now let's examine the major forms in which pollutants may exist in the atmosphere. The first form is gaseous species. Examples include sulfur dioxide, nitrogen dioxide, ozone, ammonia, and carbon monoxide. These pollutants exist in the gas phase and participate in atmospheric reactions. The second form is aqueous species. These are dissolved in cloud water, fog, rain droplets, or atmospheric moisture. Examples include hydrogen ions, sulfate ions, nitrate ions, and ammonium ions. The third form is particulate species. These species are associated with atmospheric particles. Examples include ammonium sulfate, ammonium nitrate, black carbon, mineral dust, and sulfate aerosols. The fourth form is surface species. These pollutants become adsorbed onto particle surfaces or other environmental surfaces. Surface adsorption influences transport, deposition, and chemical reactions. Now let's understand how speciation changes in the atmosphere. A pollutant released into the atmosphere rarely remains in its original form. Instead, it undergoes physical transport and chemical transformation. For example, sulfur dioxide emitted from industries can be oxidized to sulfur trioxide. Sulfur trioxide then reacts with water vapor to form sulfuric acid. Sulfuric acid may further transform into sulfate aerosols. Each stage represents a different chemical species with different environmental impacts. Similarly, nitrogen oxides can be converted into nitric acid and nitrate aerosols through atmospheric oxidation processes. This continuous transformation of species is a fundamental aspect of atmospheric chemistry. Now let's discuss why chemical speciation is important. The first reason is toxicity assessment. Different species of the same element can have different toxicities. Environmental risk depends on the specific chemical form present. The second reason is pollutant transport. Chemical species determine how pollutants move through air, water, and soil. The third reason is climate and air quality. Certain species contribute to aerosol formation, cloud processes, and atmospheric radiative balance. The fourth reason is environmental monitoring. Monitoring chemical species provides more meaningful information than measuring total elemental concentrations alone. The fifth reason is pollution control strategies. Understanding chemical transformations helps develop effective environmental management approaches. For UGC NET examinations, remember these important facts. Chemical speciation refers to the different chemical forms of an element. The same element can exhibit different environmental behavior depending on its species. Speciation controls toxicity, mobility, reactivity, transport, and environmental fate. Factors affecting speciation include pH, redox potential, temperature, sunlight, and oxidants. Sulfur, nitrogen, carbon, chlorine, and metals commonly exist in multiple atmospheric species. In this section, we will discuss the formation of inorganic particulate matter, an important topic in atmospheric chemistry and a frequently asked area in UGC NET Environmental Science. Particulate matter, commonly known as PM, refers to tiny solid particles or liquid droplets suspended in the atmosphere. These particles can originate directly from natural and anthropogenic sources or can form within the atmosphere through chemical reactions. When particulate matter is composed primarily of inorganic substances such as sulfates, nitrates, ammonium compounds, chlorides, carbonates, silicates, and metal particles, it is known as inorganic particulate matter. These particles play a significant role in air pollution, climate regulation, visibility reduction, cloud formation, and human health impacts. Let's begin by understanding the sources of inorganic particulate matter. There are two major categories: primary inorganic particulate matter and secondary inorganic particulate matter. Primary particulate matter is emitted directly into the atmosphere. Examples include dust from soil erosion, sea salt from ocean spray, volcanic ash, fly ash from thermal power plants, construction dust, mining activities, and industrial emissions. These particles enter the atmosphere already in particulate form. On the other hand, secondary particulate matter is not emitted directly. Instead, it forms in the atmosphere through chemical reactions involving gaseous precursors. Secondary inorganic aerosols constitute a major fraction of fine particulate matter, especially PM2.5. Now let's understand how secondary inorganic particulate matter forms. One of the most important precursor gases is sulfur dioxide, or SO. Sulfur dioxide is released from coal combustion, petroleum refining, industrial processes, and volcanic activity. In the atmosphere, sulfur dioxide undergoes oxidation through reactions involving hydroxyl radicals, ozone, and hydrogen peroxide. This oxidation converts sulfur dioxide into sulfur trioxide and eventually into sulfuric acid. Sulfuric acid then undergoes nucleation and condensation processes to form sulfate aerosols. These sulfate particles become an important component of atmospheric PM2.5. Another important precursor is nitrogen oxides, commonly called NOx. Nitric oxide and nitrogen dioxide are emitted from vehicle exhaust, power plants, industrial combustion, and biomass burning. Through atmospheric oxidation reactions, nitrogen dioxide is converted into nitric acid. Nitric acid subsequently participates in aerosol formation and produces nitrate particles. Nitrate aerosols contribute significantly to fine particulate matter, especially in urban and industrial regions. The third important precursor is ammonia, represented by NH. Ammonia is released primarily from agricultural activities, livestock waste, fertilizer application, and certain industrial processes. Ammonia reacts with sulfuric acid and nitric acid present in the atmosphere. These reactions produce ammonium sulfate and ammonium nitrate particles. These compounds are among the most abundant secondary inorganic aerosols worldwide. Another important pathway involves reactions between hydrogen chloride and ammonia, leading to the formation of ammonium chloride particles. Similarly, calcium ions can react with atmospheric carbon dioxide to produce calcium carbonate particles. Weathering processes also contribute silicates, metal oxides, and mineral particles to atmospheric particulate matter. Now let's examine the major types of inorganic particulate matter. The first type is sulfate aerosols, represented mainly by sulfate ions. These are formed from sulfur dioxide oxidation and contribute to acid deposition and climate effects. The second type is nitrate aerosols, formed through nitrogen oxide oxidation and nitric acid formation. The third type is ammonium aerosols, including ammonium sulfate and ammonium nitrate. These are common components of fine particulate matter. The fourth type is chloride particles, often associated with sea salt and industrial emissions. The fifth type includes carbonate particles, which originate from mineral dust and salt sources. Finally, silicates and metal particles originate from crustal materials, mining activities, industrial operations, and natural weathering processes. Now let's discuss the environmental impacts of inorganic particulate matter. The first impact is visibility reduction. Fine particles scatter and absorb sunlight, causing haze and reduced visibility. This phenomenon is commonly observed in urban and industrial regions. The second impact is acid rain formation. Sulfate and nitrate particles are closely associated with acid deposition processes. Acid rain affects forests, aquatic ecosystems, soils, and infrastructure. The third impact is human health effects. Fine particles, particularly PM2.5, can penetrate deep into the respiratory tract and even enter the bloodstream. Exposure to these particles is associated with asthma, bronchitis, cardiovascular diseases, and premature mortality. The fourth impact is climate change. Some particles scatter incoming solar radiation and exert a cooling effect. Others absorb sunlight and contribute to atmospheric warming. Therefore, inorganic aerosols play a critical role in Earth's radiative balance. The fifth impact is ecosystem disturbance. Atmospheric deposition of sulfate and nitrate particles can alter soil chemistry, nutrient balance, and water quality. These changes may affect plant growth and ecosystem functioning. Now let's discuss some important UGC NET examination points. Remember that primary particulate matter is emitted directly into the atmosphere, whereas secondary particulate matter forms through atmospheric reactions. Sulfur dioxide is the major precursor of sulfate aerosols. Nitrogen oxides are the major precursors of nitrate aerosols. Ammonia reacts with sulfuric and nitric acids to form ammonium sulfate and ammonium nitrate. Secondary inorganic aerosols are important components of PM2.5. Sulfates, nitrates, and ammonium compounds collectively account for a large fraction of fine particulate pollution in many urban regions. Let's summarize. Inorganic particulate matter consists of sulfate, nitrate, ammonium, chloride, carbonate, silicate, and metal-containing particles. These particles may be emitted directly or formed through atmospheric chemical reactions. Sulfur dioxide, nitrogen oxides, and ammonia are the most important precursor gases involved in secondary inorganic aerosol formation. Inorganic particulate matter influences air quality, climate, visibility, ecosystem health, and human well-being. Understanding these formation mechanisms is essential for pollution control and environmental management. Formation of organic particulate matter, commonly known as OPM, one of the most important topics in atmospheric chemistry and a frequently asked concept in UGC NET Environmental Science. Organic particulate matter consists of tiny particles suspended in the atmosphere that contain carbon-based organic compounds. Unlike inorganic particulate matter, which is composed mainly of sulfates, nitrates, and mineral particles, organic particulate matter contains a complex mixture of hydrocarbons, oxygenated compounds, organic acids, aldehydes, ketones, alcohols, phenols, and many other carbon-containing substances. In fact, atmospheric organic particulate matter contains thousands of different organic compounds with varying chemical properties and environmental behaviors. Organic particulate matter is a major component of PM2.5, which refers to fine particulate matter smaller than 2.5 micrometers. These particles are environmentally significant because they influence air quality, climate, visibility, cloud formation, and human health. Let's begin by understanding the two major categories of organic particulate matter. The first category is primary organic particulate matter, or primary OPM. Primary organic particles are emitted directly into the atmosphere from natural and anthropogenic sources. Examples include biomass burning, vehicle emissions, cooking emissions, industrial activities, waste burning, and forest fires. When wood, crop residues, coal, diesel, gasoline, or organic waste are burned, organic particles are released directly into the atmosphere. For example, biomass burning produces compounds such as levoglucosan, organic acids, and polycyclic aromatic hydrocarbons, commonly known as PAS. Vehicle exhaust releases alkanes, aromatic hydrocarbons, sterols, and organic carbon particles. Cooking activities emit fatty acids, aldehydes, and various organic compounds. Industrial processes release phenols, solvents, organic carbon, and PAS. These emissions contribute directly to atmospheric particulate pollution. Now let's move to the second category, which is even more important from an atmospheric chemistry perspective. This category is known as secondary organic particulate matter or secondary organic aerosol, often abbreviated as SOA. Secondary organic particulate matter is not emitted directly. Instead, it forms within the atmosphere through chemical reactions involving gaseous organic compounds. This process is called secondary formation. Volatile organic compounds, commonly called VOCs, serve as the major precursors of secondary organic aerosols. These VOCs may originate from plants, industries, vehicles, solvents, fuel combustion, and natural ecosystems. Examples include isoprene, terpenes, aromatic hydrocarbons, and alkenes. When these volatile organic compounds react with atmospheric oxidants such as hydroxyl radicals, ozone, and nitrate radicals, they undergo oxidation. The oxidation products are less volatile than the original compounds. As their volatility decreases, they begin to condense onto existing particles or form entirely new particles. This process produces secondary organic aerosols. For UGC NET examinations, remember this important sequence. VOCs, atmospheric oxidation, low volatility products, condensation, secondary organic aerosols. This pathway is one of the most important concepts in atmospheric chemistry. Now let's discuss the major mechanisms involved in secondary organic aerosol formation. The first mechanism is photochemical oxidation. Under sunlight, volatile organic compounds react with hydroxyl radicals and ozone. These reactions generate low volatility organic products that eventually become particulate matter. The second mechanism is ozonolysis. In this process, ozone reacts with alkenes and terpenes, producing carbonyl compounds, organic acids, and peroxides. These products contribute significantly to aerosol formation. The third mechanism is aqueous phase reactions. Organic compounds dissolved in cloud droplets, fog, or atmospheric moisture undergo chemical transformations. These reactions produce dicarboxylic acids and other oxygenated organic compounds. The fourth mechanism is heterogeneous reactions. In this case, gaseous organic compounds react on the surfaces of existing particles. These reactions lead to the formation of larger and more complex aerosol particles. The fifth mechanism is gas-to-particle conversion. This occurs when gaseous compounds become sufficiently low in volatility to transition into the particulate phase. Now let's examine the composition of organic particulate matter. The largest fraction typically consists of hydrocarbons, including alkanes and polycyclic aromatic hydrocarbons. Another major fraction consists of oxygenated organic compounds such as carboxylic acids, alcohols, aldehydes, and carbonyl compounds. Biomass-burning tracers such as levoglucosan and methoxyphenols are also commonly present. Additional components include nitrogen-containing compounds, sulfur-containing compounds, humic-like substances, and various secondary oxidation products. The exact composition varies depending on location, season, vegetation, industrial activity, and atmospheric conditions. Now let's discuss the environmental significance of organic particulate matter. The first impact is air quality degradation. Organic particles contribute substantially to fine particulate pollution in urban and industrial areas. The second impact is visibility reduction. These particles scatter and absorb light, causing haze and reduced visibility. The third impact is climate effects. Organic aerosols influence Earth's radiation balance by interacting with solar radiation. Some particles scatter sunlight and cool the atmosphere, while others absorb energy and contribute to warming. The fourth impact is cloud formation. Organic particles act as cloud condensation nuclei. They influence cloud properties, precipitation patterns, and atmospheric water cycles. The fifth impact is human health effects. Fine organic particles can penetrate deep into the lungs and may enter the bloodstream. Long-term exposure is associated with respiratory diseases, asthma, cardiovascular disorders, and certain cancers. The sixth impact is long-range atmospheric transport. Organic aerosols can remain suspended for extended periods and travel hundreds or even thousands of kilometers from their source. Now let's discuss some important UGC NET examination points. Primary organic particulate matter is emitted directly into the atmosphere. Secondary organic particulate matter forms through atmospheric chemical reactions. Volatile organic compounds, or VOCs, are the primary precursors of secondary organic aerosols. Hydroxyl radicals and ozone play major roles in VOC oxidation. Secondary organic aerosols may contribute a large fraction of atmospheric organic particulate matter. Biogenic VOCs released by plants, such as isoprene and monoterpenes, are important natural sources of secondary organic aerosols. Thermochemical reactions in the atmosphere, an important topic in atmospheric chemistry that helps us understand how heat energy influences chemical transformations occurring in Earth's atmosphere. Thermochemical reactions are chemical reactions that involve the absorption or release of heat energy. These reactions play a crucial role in controlling atmospheric composition, pollutant formation, climate processes, and energy balance. Every chemical reaction occurring in the atmosphere is associated with a change in energy. This energy change is represented by enthalpy, commonly denoted as delta H. If heat is released during a reaction, the reaction is called exothermic. If heat is absorbed during a reaction, the reaction is called endothermic. For UGC NET examinations, remember this important relationship. When delta H is negative, the reaction is exothermic. When delta H is positive, the reaction is endothermic. Let's first understand exothermic reactions. Exothermic reactions release heat energy into the surroundings. As a result, the surrounding environment becomes warmer. The products formed have lower energy than the reactants. Many combustion reactions occurring in the atmosphere are exothermic. For example, methane combustion can be represented as: methane reacts with oxygen to produce carbon dioxide, water, and energy. This reaction releases a large amount of heat and contributes to atmospheric warming and energy production. Another example is the oxidation of nitric oxide. Nitric oxide reacts with oxygen to produce nitrogen dioxide. This reaction releases heat and contributes to the formation of atmospheric pollutants. Now let's discuss endothermic reactions. Endothermic reactions absorb heat energy from the surroundings. As a result, the surrounding environment becomes cooler. The products formed have higher energy than the reactants. A very important atmospheric example is ozone photolysis. In this process, ozone absorbs ultraviolet radiation and breaks down into molecular oxygen and atomic oxygen. This reaction requires energy and is therefore endothermic. Ozone photolysis is a key process in maintaining the balance of ozone in the stratosphere. Now let's examine some important thermochemical reactions occurring in the atmosphere. The first reaction is the formation of nitric oxide during lightning events. At extremely high temperatures produced by lightning, nitrogen and oxygen react to form nitric oxide. This process absorbs energy and is therefore endothermic. The second reaction is sulfur oxidation. Sulfur dioxide released from industries and combustion processes undergoes oxidation to form sulfate compounds. Many of these oxidation steps release energy and contribute to atmospheric chemical transformations. The third reaction is fossil fuel combustion. Burning coal, petroleum, diesel, gasoline, and natural gas releases enormous amounts of heat and produces atmospheric pollutants such as carbon dioxide, sulfur dioxide, nitrogen oxides, and particulate matter. These reactions are strongly exothermic. The fourth reaction is biomass burning. Forest fires, agricultural residue burning, and wildfires release heat, greenhouse gases, and aerosols into the atmosphere. These reactions significantly influence regional and global atmospheric chemistry. Now let's discuss the factors affecting thermochemical reactions. The first factor is temperature. Higher temperatures generally increase reaction rates because molecules possess greater kinetic energy and collide more frequently. The second factor is pressure. Changes in atmospheric pressure can influence reaction rates, particularly for gas-phase reactions. The third factor is concentration of reactants. Higher concentrations increase collision frequency and enhance reaction rates. The fourth factor is solar radiation. Solar energy provides the activation energy required for many atmospheric reactions. Although photochemical reactions are driven directly by sunlight, thermochemical processes often interact closely with them. The fifth factor is the presence of catalysts. Certain substances lower activation energy and accelerate atmospheric reactions without being consumed. Now let's understand the environmental significance of thermochemical reactions. The first significance is atmospheric energy balance. Heat released and absorbed during atmospheric reactions influences Earth's energy budget and temperature distribution. The second significance is pollutant formation and transformation. Thermochemical reactions contribute to the formation of sulfur oxides, nitrogen oxides, particulate matter, and other atmospheric pollutants. The third significance is climate regulation. Many greenhouse gases originate from exothermic combustion processes. These emissions affect global climate and atmospheric warming. The fourth significance is air quality. Thermochemical reactions determine how pollutants are produced, transformed, and removed from the atmosphere. The fifth significance is atmospheric stability. Heat exchange influences air movement, atmospheric mixing, convection, and weather patterns. Now let's compare thermochemical and photochemical reactions. Thermochemical reactions are driven primarily by heat energy. Photochemical reactions are driven primarily by sunlight. Thermochemical processes often occur during combustion and oxidation reactions. Photochemical processes dominate ozone formation, radical generation, and smog production. Both types of reactions work together to control atmospheric chemistry. For UGC NET examinations, remember these key points. Thermochemical reactions involve heat absorption or heat release. Exothermic reactions have negative delta H values. Endothermic reactions have positive delta H values. Combustion reactions are typically exothermic. Ozone photolysis is an important endothermic process. Temperature is one of the most important factors controlling reaction rates. Thermochemical reactions influence climate, air quality, and atmospheric composition. Let's summarize. Thermochemical reactions are chemical processes associated with heat exchange. They may be exothermic, releasing heat, or endothermic, absorbing heat. These reactions regulate atmospheric energy flow, pollutant formation, climate processes, and environmental chemistry. We will study photochemical reactions in the atmosphere, one of the most important topics in atmospheric chemistry and a highly repeated area in UGC NET Environmental Science examinations. Photochemical reactions are chemical reactions that are initiated by sunlight, particularly ultraviolet radiation from the sun. Unlike thermochemical reactions, which are driven primarily by heat energy, photochemical reactions are driven by light energy. These reactions are responsible for the formation of ozone, free radicals, photochemical smog, secondary pollutants, and many atmospheric oxidation processes. In fact, photochemical reactions control a large portion of atmospheric chemistry occurring during daylight hours. Let's begin by understanding the basic principle. When sunlight strikes a molecule in the atmosphere, the molecule absorbs energy. This absorbed energy excites the molecule and may break chemical bonds. This process is called photodissociation or photolysis. The broken molecules produce highly reactive species such as atoms, ions, and free radicals. These reactive species then participate in a chain of atmospheric reactions. For UGC NET examinations, remember, photochemical reaction is equal to sunlight plus chemical transformation. Now let's understand the major steps involved in photochemical reactions. The first step is light absorption. A molecule absorbs ultraviolet radiation from the sun. The second step is excitation. The absorbed energy raises the molecule to a higher energy state. The third step is photodissociation. Chemical bonds break and reactive species are generated. The fourth step is chain reactions. The newly formed radicals react with other atmospheric molecules. The fifth step is product formation. New atmospheric compounds such as ozone, aldehydes, nitric acid, peroxy radicals, and secondary aerosols are produced. Now let's discuss some important photochemical reactions occurring in the atmosphere. The first and most important reaction involves nitrogen dioxide photolysis. Nitrogen dioxide absorbs sunlight and decomposes into nitric oxide and atomic oxygen. The atomic oxygen produced is highly reactive. It immediately reacts with molecular oxygen in the presence of a third body to form ozone. This reaction is one of the major pathways for ozone formation in the troposphere. The second important reaction is ozone photolysis. Ozone absorbs ultraviolet radiation and breaks down into molecular oxygen and atomic oxygen. This reaction plays a crucial role in maintaining the ozone balance in the atmosphere. The third important reaction is water vapor photolysis. Under high-energy radiation, water molecules can produce hydroxyl radicals. Hydroxyl radicals are among the most important oxidizing agents in atmospheric chemistry. Remember this important UGC NET fact. Hydroxyl radical, or is known as the detergent of the atmosphere. It removes many pollutants and helps maintain atmospheric cleanliness. Now let's discuss the major free radicals involved in photochemical reactions. The first is the hydroxyl radical, or. This radical initiates the oxidation of pollutants and greenhouse gases. The second is the hydroperoxyl radical, O. It participates in ozone formation and atmospheric oxidation cycles. The third is the organic peroxy radical, represented as Rho. These radicals form during the oxidation of volatile organic compounds. The fourth group includes chlorine and bromine radicals. These radicals are important because they contribute to stratospheric ozone depletion. The fifth species includes excited oxygen atoms such as O1d and O3t. These highly reactive oxygen species are central to ozone chemistry. Now let's understand the formation of photochemical smog. Photochemical smog develops when sunlight acts on nitrogen oxides and volatile organic compounds, commonly called VOCs. The major sources of nitrogen oxides include vehicles, industries, thermal power plants, and fossil fuel combustion. The major sources of VOCs include fuel evaporation, industrial solvents, biomass burning, and vegetation. Under sunlight, nitrogen dioxide undergoes photolysis and produces atomic oxygen. Atomic oxygen reacts with oxygen molecules to form ozone. At the same time, VOCs generate organic peroxy radicals. These radicals convert nitric oxide back into nitrogen dioxide without consuming ozone. As a result, ozone accumulates in the lower atmosphere. This process leads to the formation of photochemical smog. The major components of photochemical smog include tropospheric ozone, peroxyacetyl nitrate or PAN, aldehydes, organic nitrates, secondary organic aerosols, and various oxidizing compounds. Now let's discuss the environmental significance of photochemical reactions. The first significance is ozone formation. Photochemical reactions control both the formation and destruction of ozone. The second significance is atmospheric self-cleansing. Hydroxyl radicals generated through photochemical processes oxidize and remove pollutants. The third significance is photochemical smog formation. Urban air pollution problems are largely driven by photochemical reactions. The fourth significance is secondary pollutant production. Many pollutants are not emitted directly but are formed through photochemical transformations. The fifth significance is climate influence. Photochemical processes affect greenhouse gases, aerosols, and atmospheric radiative balance. The sixth significance is human health effects. Ozone and photochemical oxidants can damage respiratory tissues and aggravate asthma and lung diseases. Now let's discuss factors affecting photochemical reactions. The most important factor is sunlight intensity. Stronger ultraviolet radiation increases photochemical activity. Temperature also influences reaction rates. Higher concentrations of nitrogen oxides and VOCs promote ozone and smog formation. Meteorological conditions such as wind speed, humidity, and atmospheric stability also affect photochemical processes. This is why photochemical smog is more common during warm, sunny, and stagnant weather conditions. For UGC NET examinations, remember these important points. Photochemical reactions are initiated by sunlight. Nitrogen dioxide photolysis is the key step in tropospheric ozone formation. Hydroxyl radicals are known as the detergent of the atmosphere. Photochemical smog forms through reactions involving nitrogen oxides, VOCs, and sunlight. Ozone is beneficial in the stratosphere but harmful in the troposphere. Photochemical reactions produce secondary pollutants such as ozone and PAN. Oxygen chemistry and ozone chemistry. Oxygen is one of the most abundant and chemically active elements in Earth's atmosphere. It plays a crucial role in respiration, combustion, atmospheric oxidation, and the formation of ozone. The chemistry of oxygen controls many atmospheric processes and helps maintain life on our planet. Let us begin by understanding the major oxygen species present in the atmosphere. The most abundant form is molecular oxygen, represented as O. It constitutes approximately 20.95% of the atmosphere and is essential for respiration and oxidation reactions. Another important form is ozone, represented as O. Ozone is a triatomic molecule composed of 3 oxygen atoms. Although present in very small concentrations, it has enormous environmental significance. We also find highly reactive forms such as atomic oxygen and oxygen radicals, which participate in atmospheric chemical reactions. Now let's understand ozone. Ozone is a powerful oxidizing agent and is found in 2 distinct regions of the atmosphere. The first is the stratosphere, where ozone forms the ozone layer. This ozone is often called good ozone because it protects life on Earth by absorbing harmful ultraviolet radiation from the sun. The second is the troposphere, where ozone acts as an air pollutant. This ozone is often called bad ozone because it contributes to photochemical smog and causes adverse health effects. For UGC NET examinations, always remember: stratospheric ozone is equal to good ozone. Tropospheric ozone is equal to bad ozone. Now let us study how ozone is formed in the atmosphere through the Chapman mechanism. The Chapman mechanism explains the natural formation and destruction of ozone in the stratosphere. The first step is the photodissociation of oxygen. When ultraviolet radiation with wavelengths less than 242 nanometers strikes molecular oxygen, the oxygen molecule splits into two oxygen atoms. These atomic oxygen species are highly reactive. In the second step, atomic oxygen reacts with molecular oxygen in the presence of a third body, usually nitrogen or oxygen molecules. This reaction produces ozone. Thus, ozone is continuously formed in the stratosphere through solar radiation-driven reactions. However, ozone is not permanently stable. It is also continuously destroyed. When ozone absorbs ultraviolet radiation, it breaks down into molecular oxygen and atomic oxygen. This process is known as ozone photolysis. As a result, ozone formation and ozone destruction occur simultaneously, creating a dynamic balance known as the ozone-oxygen cycle. This cycle is essential for maintaining the concentration of ozone in the stratosphere. Now let's discuss the environmental importance of stratospheric ozone. The ozone layer absorbs most harmful ultraviolet B and ultraviolet C radiation from the sun. Without this protective shield, life on Earth would be exposed to dangerous levels of ultraviolet radiation. Excessive UV exposure can cause skin cancer, cataracts, immune system suppression, reduced crop productivity, and damage to aquatic ecosystems. Therefore, the ozone layer acts as Earth's natural sunscreen. Now let's discuss ozone depletion. Ozone depletion occurs when ozone molecules are destroyed faster than they are formed. The major cause of ozone depletion is the release of ozone-depleting substances such as chlorofluorocarbons, commonly known as CFCs. When CFCs reach the stratosphere, ultraviolet radiation breaks them apart and releases chlorine radicals. These chlorine radicals initiate catalytic reactions that destroy ozone molecules. A single chlorine atom can destroy thousands of ozone molecules before being removed from the atmosphere. Similarly, bromine radicals released from halogens are even more effective at ozone destruction. Nitrogen oxides and hydrogen radicals also participate in ozone depletion cycles. For UGC NET examinations, remember, CFCs release chlorine radicals, which catalytically destroy ozone. Now let's move to oxygen chemistry involving free radicals. One of the most important species is the hydroxyl radical, represented as O. The hydroxyl radical is known as the detergent of the atmosphere because it reacts with pollutants and greenhouse gases, helping remove them from the atmosphere. O radicals participate in oxidation reactions involving methane, carbon monoxide, sulfur dioxide, nitrogen oxides, and volatile organic compounds. Hydroperoxyl radicals and organic peroxy radicals are also important components of atmospheric oxygen chemistry. Together, these radicals control atmospheric oxidation capacity and influence air quality. Now let's discuss the impacts of oxygen and ozone chemistry. The first impact is protection from ultraviolet radiation through the ozone layer. The second impact is atmospheric self-cleansing, achieved through hydroxyl radical-mediated oxidation processes. The third impact is air quality regulation, since ozone and radicals influence pollutant transformation. The fourth impact is climate regulation, because ozone acts as a greenhouse gas and affects Earth's radiation balance. The fifth impact is human health, as excessive tropospheric ozone can irritate the respiratory system and aggravate asthma. Now let's discuss some important UGC NET points from this topic. Molecular oxygen constitutes about 21% of Earth's atmosphere. Ozone is formed through the Chapman mechanism. Stratospheric ozone absorbs harmful UV radiation. Tropospheric ozone is a secondary pollutant and a major component of photochemical smog. Hydroxyl radicals are known as the detergent of the atmosphere. CFCs release chlorine radicals that destroy ozone through catalytic cycles. Ozone depletion increases the amount of ultraviolet radiation reaching Earth's surface. Of radicals participate in oxidation reactions involving methane, carbon monoxide, sulfur dioxide, nitrogen oxides, and volatile organic compounds. Hydroperoxyl radicals and organic peroxy radicals are also important components of atmospheric oxygen chemistry. Together, these radicals control atmospheric oxidation capacity and influence air quality. Now let's discuss the impacts of oxygen and ozone chemistry. The first impact is protection from ultraviolet radiation through the ozone layer. The second impact is atmospheric self-cleansing, achieved through hydroxyl radical-mediated oxidation processes. The third impact is air quality regulation, since ozone and radicals influence pollutant transformation. The fourth impact is climate regulation, because ozone acts as a greenhouse gas and affects Earth's radiation balance. The fifth impact is human health, as excessive tropospheric ozone can irritate the respiratory system and aggravate asthma. Now let's discuss some important UGC NET points from this topic. Molecular oxygen constitutes about 21% of Earth's atmosphere. Ozone is formed through the Chapman mechanism. Stratospheric ozone absorbs harmful UV radiation. Tropospheric ozone is a secondary pollutant and a major component of photochemical smog. Hydroxyl radicals are known as the detergent of the atmosphere. CFCs release chlorine radicals that destroy ozone through catalytic cycles. Ozone depletion increases the amount of ultraviolet radiation reaching Earth's surface. Photochemical smog is a type of air pollution that forms when sunlight reacts with nitrogen oxides, commonly known as NOx, and volatile organic compounds, known as VOCs. It is most commonly observed in urban and industrial regions where vehicle emissions, industrial activities, and strong sunlight occur together. Unlike classical smog, which is associated with sulfur dioxide and smoke, photochemical smog is formed through sunlight-driven chemical reactions. For this reason, it is often called oxidizing smog or Los Angeles-type smog. Let us understand the formation mechanism of photochemical smog. The process begins with the emission of nitrogen oxides from vehicles, power plants, industries, and fuel combustion. At the same time, volatile organic compounds are released from fuel evaporation, industrial solvents, paints, biomass burning, and vegetation. When sunlight reaches the atmosphere, nitrogen dioxide absorbs ultraviolet radiation and undergoes photolysis. Nitrogen dioxide breaks down into nitric oxide and atomic oxygen. The atomic oxygen then reacts with molecular oxygen to form ozone. This is the first major step in smog formation. At the same time, volatile organic compounds react with hydroxyl radicals and other oxidants. These reactions generate organic peroxy radicals. The peroxy radicals convert nitric oxide back into nitrogen dioxide without consuming ozone. As a result, ozone accumulates continuously in the lower atmosphere. This accumulation of ozone and other oxidizing pollutants leads to the formation of photochemical smog. For UGC NET examinations, remember this important equation. Photochemical smog is equal to nitrogen oxides plus volatile organic compounds plus sunlight. Now let's examine the major components of photochemical smog. The first and most important component is tropospheric ozone, represented as O. Ozone is the major oxidant present in photochemical smog. It irritates the respiratory system and damages vegetation. The second component is peroxyacetyl nitrate, commonly known as PAN. PAN is a secondary pollutant formed during photochemical reactions involving nitrogen oxides and organic compounds. It causes eye irritation and plant damage. The third component consists of nitrogen dioxide and other nitrogen oxides. These gases contribute to atmospheric oxidation and respiratory problems. The fourth component is aldehydes, including formaldehyde and acetaldehyde. These compounds irritate the eyes, nose, and throat. The fifth component includes peroxy radicals, which drive the chain reactions responsible for smog formation. The sixth component consists of secondary organic aerosols, which contribute to fine particulate pollution and visibility reduction. Now let's discuss the conditions that favor photochemical smog formation. The first requirement is strong sunlight. Photochemical reactions require solar radiation to initiate pollutant transformations. The second requirement is high temperature. Warm conditions increase reaction rates and promote smog formation. The third requirement is stagnant air conditions. Low wind speeds prevent pollutant dispersion and allow pollutants to accumulate. The fourth requirement is temperature inversion. A temperature inversion traps pollutants near the Earth's surface, enhancing smog development. The fifth requirement is the presence of abundant nitrogen oxides and volatile organic compounds. Urban and industrial regions provide these precursor pollutants in large quantities. This is why photochemical smog is especially common during summer months in major metropolitan cities. Now let's compare classical smog and photochemical smog. Classical smog, also called sulfurous smog or London smog, is formed primarily from sulfur dioxide and smoke. It usually occurs during cold and humid weather conditions. Photochemical smog, on the other hand, forms from nitrogen oxides and volatile organic compounds under sunny and warm conditions. Classical smog is reducing in nature, whereas photochemical smog is oxidizing in nature. For UGC NET examinations, understanding this distinction is very important. Now let's examine the environmental and health effects of photochemical smog. The first effect is on human health. Photochemical smog irritates the eyes, nose, throat, and respiratory tract. Exposure may cause coughing, breathing difficulty, asthma aggravation, bronchitis, and reduced lung function. Long-term exposure can increase the risk of respiratory and cardiovascular diseases. The second effect is on vegetation. Ozone and PAN damage plant tissues and reduce photosynthesis. This results in decreased crop productivity and reduced plant growth. Sensitive crops such as soybean, wheat, cotton, and tobacco are particularly affected. The third effect is on visibility. Secondary aerosols formed during smog episodes scatter light and create haze. This reduces visibility in urban and industrial regions. The fourth effect is on materials and infrastructure. Photochemical oxidants damage rubber, plastics, paints, fabrics, and building materials. The fifth effect is on climate. Tropospheric ozone acts as a greenhouse gas and contributes to global warming. The sixth effect is on ecosystems. Smog-related pollutants can alter ecosystem processes, nutrient cycling, and biodiversity. Now let's discuss control measures for photochemical smog. The most effective strategy is reducing emissions of nitrogen oxides and volatile organic compounds. This can be achieved through cleaner fuels, improved combustion technologies, catalytic converters in vehicles, industrial emission controls, and strict environmental regulations. Increasing public transportation use and reducing fossil fuel dependence also help decrease precursor emissions. Urban greening and afforestation can contribute to improved air quality. Environmental monitoring programs are essential for identifying high-risk pollution periods and implementing control measures. Now let's review some important UGC NET points. Photochemical smog is formed by reactions between nitrogen oxides, volatile organic compounds, and sunlight. Tropospheric ozone is the major oxidant present in photochemical smog. Peroxyacetyl nitrate, or PAN, is a characteristic component of photochemical smog. Photochemical smog is most common during warm, sunny, and stagnant weather conditions. It causes respiratory problems, plant damage, visibility reduction, and material deterioration. Photochemical smog is also known as Los Angeles-type smog. Let's summarize. Photochemical smog is a secondary air pollutant formed through sunlight-driven reactions involving nitrogen oxides and volatile organic compounds. The major products include ozone, TAN, aldehydes, peroxy radicals, and secondary organic aerosols. Photochemical smog affects human health, vegetation, visibility, climate, and ecosystems. Understanding its formation and impacts is essential for air pollution control and environmental management. Volatile organic compounds, nitrogen oxides, and peroxyacetyl nitrate, commonly known as VOCs, NOx, and PAN. These compounds are closely connected and play a central role in the formation of photochemical smog. Questions related to these concepts frequently appear in UGC NET Environmental Science examinations, making this topic extremely important from an examination perspective. Let us begin with volatile organic compounds, or VOCs. VOCs are carbon-containing compounds that easily evaporate into the atmosphere under normal environmental conditions. These compounds originate from both natural and anthropogenic sources. Natural sources include forests, vegetation, and biological processes. Plants release compounds such as isoprene and terpenes into the atmosphere. Anthropogenic sources include vehicle emissions, industrial activities, fuel combustion, solvent use, paint industries, petroleum refineries, and biomass burning. Common examples of VOCs include methane, benzene, toluene, xylene, isoprene, and formaldehyde. Although VOCs may exist in low concentrations, they are extremely important because they participate in atmospheric oxidation reactions. When VOCs react with hydroxyl radicals, ozone, and nitrogen oxides, they produce a variety of secondary pollutants. These reactions contribute to the formation of ozone and secondary organic aerosols. For UGC NET examinations, remember, VOCs are major precursors of photochemical smog and secondary organic aerosols. Now let us move to nitrogen oxides, commonly called NOx. The term NOx mainly refers to two gases: nitric oxide, represented as NO, and nitrogen dioxide, represented as NO. These gases are produced primarily during high-temperature combustion processes. Major sources include vehicle exhaust, thermal power plants, industrial boilers, biomass burning, and fossil fuel combustion. When fuel burns at high temperatures, atmospheric nitrogen reacts with oxygen to form nitric oxide. Nitric oxide is then oxidized to nitrogen dioxide. Among these two gases, nitrogen dioxide plays a particularly important role in atmospheric chemistry. When sunlight strikes nitrogen dioxide, it undergoes photolysis and produces nitric oxide and atomic oxygen. The atomic oxygen then reacts with molecular oxygen to form ozone. This process represents the key step in tropospheric ozone formation. For UGC NET examinations, remember this important fact. No photolysis is the key step in the formation of tropospheric ozone. In addition to ozone formation, nitrogen oxides also contribute to acid rain and photochemical smog. Therefore, NOx compounds are among the most important atmospheric pollutants. Now let us discuss PAN, or peroxyacetyl nitrate. PAN is a secondary pollutant. Unlike primary pollutants, PAN is not emitted directly into the atmosphere. Instead, it forms through photochemical reactions involving VOCs and nitrogen oxides in the presence of sunlight. Its chemical formula is CH2. PAN is produced when organic peroxy radicals react with nitrogen dioxide. This process commonly occurs during photochemical smog episodes. One unique characteristic of PAN is its ability to act as a reservoir for nitrogen oxides. It can transport reactive nitrogen compounds over long distances and release them later under favorable atmospheric conditions. This allows smog-related pollutants to spread far away from their original source regions. PAN is also highly toxic to vegetation. It damages plant tissues, reduces photosynthesis, and decreases crop productivity. In humans, PAN causes irritation of the eyes and respiratory tract. For this reason, PAN is often considered one of the most characteristic pollutants associated with photochemical smog. For UGC NET examinations, remember, PAN is the characteristic pollutant of photochemical smog. Now let us understand the relationship between VOCs, NOx, and PAN. These compounds are chemically interconnected. First, VOCs and NOx are released into the atmosphere from natural and anthropogenic sources. Under the influence of sunlight, VOCs undergo oxidation reactions and generate organic peroxy radicals. These radicals react with nitrogen oxides and initiate a series of photochemical reactions. As a result, ozone is formed. Simultaneously, PAN and several other secondary pollutants are produced. Therefore, the complete process can be summarized as VOCs plus NOx plus sunlight produce ozone, PAN, and photochemical smog. This relationship is one of the most important concepts in atmospheric chemistry. Let us now discuss the environmental significance of these pollutants. VOCs contribute to ozone formation and secondary organic aerosol production. NOx contributes to ozone formation, acid rain, and photochemical smog. PAN contributes to vegetation damage, eye irritation, and long-range transport of reactive nitrogen compounds. Together, these pollutants influence air quality, climate processes, ecosystem health, and human well-being. They are major concerns in urban and industrial environments worldwide. Now let's revise some important UGC NET facts. VOCs are volatile carbon-containing compounds. NOx mainly consists of nitric oxide and nitrogen dioxide. Nitrogen dioxide photolysis initiates ozone formation. PAN is a secondary pollutant. PAN is the characteristic pollutant of photochemical smog. VOCs and NOx are precursors of ozone and photochemical smog. The fundamental atmospheric chemistry relationship is VOCs plus NOx plus sunlight ozone plus PAN plus photochemical smog. Let's summarize. Volatile organic compounds, nitrogen oxides, and peroxyacetyl nitrate are among the most important atmospheric pollutants. VOCs and NOx serve as precursor pollutants, while PAN is a secondary pollutant formed through photochemical reactions. Their interactions drive ozone formation, photochemical smog development, and secondary aerosol production. A strong understanding of these concepts is essential for mastering atmospheric chemistry and performing well in UGC NET Environmental Science examinations.